In this recording, we're going to look at inverses of radical functions. Now, as it says here in the introduction, the idea of inverses or opposites is very important. You might think about the inverse of taking off your shoe being putting on your shoe, or the inverse of driving to school as driving home from school. Okay, so operations such as multiplication and division and things like that have inverses, undoing operations. And functions can also have inverses. And that's what we're going to study here, inverses of the radical function. So let's specifically look at the relationship between x squared and the square root of x. You obviously know that they undo each other. If I want to get rid of a square or a square root, I can use the other function to undo it. So let's complete this table of values, and then I want you to comment on what you notice. I want you to do this without a calculator. There's no way you need a calculator to do this work. So pause the recording, play it when you're ready. Okay, so hopefully you took the time to enter these values. So obviously these squared, you've got these. Now when it comes to square rooting the negatives, we cannot. These would result in imaginary numbers. So I'm just going to put a line through here. These cannot be square rooted and result in real numbers. Obviously they are imaginary. Okay, and hopefully you commented on what you noticed here. There's a lot of things you might have noticed. If you haven't noticed anything, take a moment. Okay, so hopefully you noticed something about the switching of the x's and y's for the positive values of x and y. Okay, obviously we didn't result in any negative values here. But if I just look at those 0, 1, 4, 9, the y's became the x's and vice versa. Now I'm going to introduce you to something here called composition of functions. All right, and that's going to allow us to justify this and hopefully make a little sense of this. I want you to think about your experience driving to school and then driving home from school. So if you drive to school and then you drive home from school, you end up where you started. If you put on your shoe and then you take off your shoe, you end up where you started, right, with no shoe on. And so this is a similar deal here. We're going to compose of functions. We're going to do what we call f of g of 9. And for some of you that's looking at like, what? That's crazy. I'll never be able to do that. You can. Just ignore the f, pretend that's not there, and just do g of 9. So g means square root it. So square rooting the 9, we get 3, right? And now we're going to do f of that 3. Okay, so initially we ignored the f until we had evaluated what's inside. Just think about your order of operations. Do what's in the parentheses first. So g of 9 we knew was square root of 9, which is 3. And now we're going to do f of 3. Okay, so f function is square, and we do 3 squared, we get 9. Okay. I want you to do something similar here with g of f of 2. Take a moment, try to figure it out, and then play the recording when you're ready. Okay, so hopefully you thought about this. You ignored the g for now. Just pretend it's not there. F of 2. Well, f function says square it. So we've got 4, right? And now we're going to do g of 4. I can erase that squiggle. And then obviously g of 4 means square root the 4, so we're back to 2. So I'm hoping you made a connection here. When we compose functions and their inverses, we get back to the original input value. And I'll write that out. Okay, so we talked here about undoing operations, just like driving to school, driving home from school. Okay, a little illustration here. It demonstrates a few things related to the domain and range. Obviously, domain is the input, range the output. Well, when we have inverses, the domain of, for example, the x squared function, the x's, becomes the set of the y values, or the range of its inverse, the square root, right? The x set of x's became the set of y's. Okay? And when we do f of a, we get b, like meaning we do right here f of a, pick an a value like 2. Square of 2, you get 4. The square root of 4, you get back to 2. And that's what we're identifying here. Okay. F of a, you get b. G of b, you get a, so long as f and g are inverses. All right. This next page, we're going to identify some vocabulary here and make some connections with the graph and the algebra. Okay. Now, this is familiar notation from before. When we write the inverse, we write it with a little -1 superscript. Right? It's not an exponent, but it's just notation that allows us to identify that this new function that we're going to create is the inverse of this function that has the same name, f. And we read it as the inverse of f of x. So read that out loud, the inverse of f of x. Not every function has an inverse that is a function. Okay? And it's only one-to-one functions that have inverses that are functions. Okay? They have to pass the horizontal line test to be 1, 2, 1. All right. So let's look at a graphical relationship here. Similar function, we've got our x squared function. We've got a table of values. Now, in order to find the inverse of f of x, we're going to switch the x and y's. So this set of x's becomes our y's. This set of y's becomes our x's. So go ahead and complete that table. Make a graph for the inverse of f of x. Okay, so hopefully you did that, and this is what it would look like. Okay, so hopefully you made that graph labeled both the original function and its inverse. What do you notice about that graph of the inverse? So just take a second to observe it. Okay, so hopefully you identify that that's not a function, right? That inverse of f of x is not a function. Let's make that note. Now sometimes we have a function, f of x, for example, that produces an inverse that is not a function. And what we want to do is make it certain that the inverse is a function. So what we're going to do is restrict the domain of the original function. That's what we're talking about here. In this case, if I take this portion here, this right side of the parabola, okay, and I just restrict it, you can take a color or something and just kind of color that in, shade that a little bit. Mine's gotten a little messy. I have a little technical issue here. Okay, but if we restrict it just to the portion where the x is greater than or equal to 0, that means when we invert it, we're just going to have this portion of the graph that is the inverse, which would obviously be a function, as opposed to this portion of the relation, which fails the vertical line test. Okay. And then I also want you to, as it says here, draw in the dotted line y equals x. Okay? So we'll make that dotted line. Go corner to corner on this. Okay. So got the dotted line y equals x. That will always be a line of symmetry, and we can label it. Oh, I've got a funky little, that's funny. That will always be the line of symmetry that corresponds to the two inverse functions. Okay? So the relationship between f of x and its inverse is, graphically, they're symmetrical across the line y equals x. Thanks for watching.